Hello everyone. On this video we will be looking at the continuous growth and decay formula. Okay, so if we have our continuous growth formula, that's A of t is equal to P times e to the power of RT. Okay, now in this case your principal or initial value is your P. Okay, so your rate of growth or decay, depending on the problem, is your R, and remember you're going to convert any percentages to decimals. Your T represents time. Now time could be minutes, hours, seconds, days, years, any at all. Okay, and our A of T equals the amount of times after T, or amount of T after units of time, T units of time. So how much do you have after 4 hours? Or how much do you have after 8 hours? Or how much do you have after 3 days? Or something like that. Okay. Now, if your rate of growth is positive, which is exponential growth, you're going to use the formula A of t is equal to P times e to the power of RT. Now, if you're experiencing decay in your problem, okay, so your rate of growth is less than 0, or it's decreasing at a negative rate, then your exponential decay formula is the same thing, except your rate is going to be negative. It's A of t equals your principal times e to the power of negative r times t. Okay, so it's pretty much one formula to remember, but one's positive for growth and one's negative for decay, or any type of decline. All right, so if you are still writing this, of course, feel free to press pause and finish up. But we're going to go ahead and move on to our first example. Okay, so let's say a person invested $1,000 into an account earning 10% per year compounded continuously. How much was in the account at the end of 1 year? Okay, now this is probably what you're used to using it for. So we're going to go ahead and do this, and then we're going to see how we're going to apply the same continuous formula to other problems. Okay, so now this is going to grow. It's not going to decline as time goes on. It's going to grow at a rate of 10%. So we know that we're going to use A of t equals P times e to the RT, since we know it's growing. In this case, our principal is $1,000. Remember, that's your starting value. Or sometimes it's called the initial value or principal value. Your R is equal to 10%, which is your interest rate that it's growing, which is 0.10 once we convert it to a decimal. And your T is equal to 1 because we're looking at 1 year. All right. So if we go ahead and plug all of those in, if T is equal to our principal, which is 1,000, times e to the power of your rate, which is 0.10, or you could just put 0.1, times your time, which is t equals 1. So we go ahead and replace that. So actually this ends up being 1,000 times e to the 0.10 times 1 is just 0.1. Plug that into your calculator, and your amount is equal to $1,105.17. Okay, so if you invest $1,000 into an account earning 10% per year compounded continuously, that's how much you would have at the end of the year. All right. So if you are still writing, feel free to press pause. But now we're going to look at how we're going to use these formulas for other types of problems. Okay. So what if we have a radioactive substance that has a decay rate of 0.044 grams per hour? How many grams of a 100 gram sample will remain radioactive after 2 hours? Okay, so hint, this is a decay problem, so we're going to use the negative R. All right, so what I want you to do is go ahead and press pause and try to solve this one on your own. All right, so since we know it's a decay problem, again, just rewriting that. Principal times e to the negative RT. Okay, so we know our principal is 100 grams. Remember, that's what we started with. Our rate, it's already in the decimal, so we don't have to convert it. So it's negative 0.044. Remember, it's decaying, so it's going to be negative. And our time is equal to 2 hours, or just 2. All right, so if we go ahead and plug it in, our principal is 100 times E to the negative R, so that's negative 0.044 times T, which is 2. Okay, so if we plug all of that in e to the, remember that's e to the power of this. So we plug all of that into your calculator, is going to equal, well, it's going to be approximately 91.6 grams. Okay, so always remember, this is e to the power of this here. Okay, you don't want to just go e times this. You want to go e to the power of this value, then multiply that by 100. All right, so if you are still writing, again, feel free to press pause and finish up. But we're going to go ahead and move on to our next example. Now, this one is a little bit tricky, but if you understand the concept of each of the parts of the continuous growth and decay formula, it'll make sense. But what I want you to do, first let me read it out. So you have a sample bacteria is growing at a rate of 8% per hour, compounded continuously. How many hours will it take for the sample to double? Okay. Now, believe it or not, everything you need to solve this problem is already given. So what I want you to do is go ahead and press pause and see if you can figure this one out on your own. All right, so assuming you've pressed pause and worked this one out, so what we're going to do over here, we're going to kind of start our setup. Okay, so what's the number of sample bacteria? We have no idea how many sample bacteria we have. So when you don't know, you just give it a variable x. Now, what's the double that number? Well, that's just 2 times x. Okay. So remember, we're going with a sub x, oh, not a sub x. Or you can go a of x, a of t, pe to the rt. So let's change that x to t so our variables match. There we go. Okay. Now remember, this is your amount after whatever time, and your principal is your starting value. Okay. So we don't know what our starting value is, so we have x. So our p turns to x, and we want to find out our final number is double that. So the amount will be 2x. So we have our final amount equals our principal times e to the power of RT. Okay, but we have our rate. I'm going to go ahead and put that over here. Our rate is equal to 8%, which is 0.08. So that gives us 2x equals x e to the 0.08 times our time, which is unknown. That's what we're trying to figure out. How long will it take? So that's times t. Okay. Now, if we divide both sides by x, let me draw the little step arrows there. Okay, so those two cancel and those two cancel. You have 2 equals e to the power of 0.08 t. Okay, so now remember, the natural log of e to the power of x is just equal to x. The natural log and the e cancel each other out. So what we're going to do is we're going to apply the natural log to both sides. Okay, so you have the natural log of 2 is equal to the natural log of e to the 0.08 t power. Okay, so we know that the natural log of e to the power of x, that just makes that x. Also, we know that the natural log of x to the power of whatever number is equal to that number times the natural log of x. Which means we're going to get this, the natural log of that number, and bring it down. So you have the natural log of 2, let me bring that up, there we go, equals 0.08 times t times the natural log of e. Okay. Now e is just e to the first power. So the natural log of e to the first power, or natural log of e, is just equal to 1. So that gives us natural log of 2 equals 0.08 t. Now we divide both sides by 0.08. So natural log of 2, sorry about that, divided by 0.08 is equal to t. So if you plug this into your calculator, you will end up with t is approximately equal to 8.66. But we want to round it to the nearest whole number, so that's 9 hours after it's rounded. All right. So if you are still writing, feel free to press pause and finish up. But we're going to go ahead and move on to our next example. Oops. If I can get the paper, there we go. Okay. Once again, this one's a little bit tricky, but if you understand the actual concepts, it's not undoable. Well, it's not impossible. I'll put it that way. Not undoable. It's not impossible. Okay, so we have a small object with an initial temperature of 135 degrees Fahrenheit that is dropped into a tub with a temperature of 60 degrees Fahrenheit. The function f of t equals c times e to the power of negative kt plus 60 represents the situation where t is your time in minutes, C is a constant, and K is a constant. Okay. Now, after 6 minutes, the object has a temperature of 85 degrees. What is the approximate value of K? Okay, so we're going to solve for K on this one. All right. So again, this is tricky, but what I want you to do is go ahead and press pause and try to solve this one on your own. All right, so I'm assuming you've paused it and worked it out. So let's go ahead and verify your answer. Okay, so we see here, just going to compare our formulas. So you have A of t equals P times e to the RT power. And we're going to compare that to our F of t is equal to C times e to the negative KT. Oh, that should be negative. There we go. Plus 60. Okay, so again, this is our amount after a certain amount of time. We just changed the variable, so this is now our amount after a certain time. P is our principal or starting value. In this case, it's going to be C. Remember, the variables can change. Okay, as long as you have the same general format or the idea, the variables aren't that important. And as you get more practice in, you'll be able to apply this using different variables. But if you want to continue using this until you get comfortable, that's okay. Just remember to apply them evenly so you don't forget that your P is your C or your A of t is your F of t. Okay, so in this case, we know our initial value is when your time is equal to 0. Okay, that's before the time is moved. You want to know, okay, before we started counting, where were we? Well, we know that when t is equal to 0, then the object is 135 degrees. Well, what does that tell us? That tells us that f of 0 is equal to 135. When t is 0, your y will be 135. So if we apply that, let me go ahead and separate that a little bit. Okay, so f of 0 just means that we get this and turn all of our t's to 0. So f of 0 just means you have c times e to the negative k times 0 is just 0. So the 0 plus 60 equals 135. Okay, so remember, this is your f of 0, and that's equal to 135. Okay, so e to the power of 0 is just 1. So if we subtract 60 from both sides, we have 1 times c, which is just c, is equal to 135 minus 60, which is 75. .35 minus 60 equals 75, and e to the power of 0 is equal to 1. Okay, just little side notes here, so you're not trying to figure out how did you get that from that. So remember, that just turned to 1. We subtract 60 from both sides, got our 75. All right, so now we can look at this part of the problem. Okay, after 6 minutes, we want to know what the temperature of the object is. Well, it's at 85 degrees. We want to know the approximate value of our K. All right, so let me straighten it up. There we go. After 6 minutes, the object is 85 degrees. So what does that mean? That means f of 6 is equal to 85. Okay, so what we do here is we get our, let me move this down just a little bit, our formula here, and we replace t with 6. So once again, we know our initial value, initial temperature, or in this case, C is going to equal 75. So we have 75 e to the negative 6 times k plus 60 is equal to 85. Okay, remember, we just solved for C here. So f of t is equal to c e to the negative kt plus 60. So I don't have to keep moving this up and down. So all we did, once again, is replace our t with 6 and our c with what we already solved. So that's how we got the 75 e to the negative 6 times k plus 60 equals 85. F of 6, which is this, equals 85. Okay, so once again, if we subtract 60 from both sides, we have 75 e to the negative 6k equals 25. So if we divide both sides by 75, we get 25 over 75 over here, which simplifies to 1/3. So you have e to the negative 6k equals 1/3. All right, now once again, we apply natural log to both sides, because we want to get that negative 6k down. All right, so let me straighten up the paper there. I'm just going to move that over. Natural log of e to the negative 6k is equal to the natural log of 1/3. Now, using the power rule for logarithms, that negative 6k comes down to the front. Negative 6k times the natural log of e is equal to the natural log of 1/3. Remember, natural log of e is just 1. So if we divide both sides by negative 6, we have k is equal to the natural log of 1/3 divided by negative 6. So if you plug that into a calculator, it will be approximately 0.183 for your value of k. All right. So if you are still writing, of course, feel free to press pause, but we're going to go ahead and move on to our next problem. All right. So what if we have a sample of bacteria that is decaying according to the half-life model, f of t equals n times e to the power of negative 0.226 times t, where n is your initial sample size and t is the time in hours. At t equals 4, there are 25 bacteria remaining. What was the initial sample amount? And you want to round that to the nearest whole number. All right, so what I want you to do is go ahead and press pause again and try to solve this one on your own. All right, so I'm assuming you've paused it. And let's go ahead and verify. Okay, so again, you have your A of t is equal to P times E to the negative K T. All right, so for this one, you know you have your F of t is equal to N times E to the negative KT. Okay, remember, for these, you don't have a rate. So in this case, your R is just negative K. They replace that since you're not looking at the rate. So instead of at R, you're looking at K. All right. So we have our time is equal to 4 hours. And our amount is equal to 25 bacteria. Remember, we just don't know what the initial sample size is. So we don't know what N is. We know what the amount is after 4 hours, but we don't know what we started with. So we have to find what we started with. All right, so our F of T is equal to 25. So we have 25 is equal to N times E. We have negative 0.226 times our time T, which is 4. Okay. So if we divide both sides by e to the power of negative 0.226 to the power of 4, we end up with 25 over e. We multiply those two together, we get to the power of negative 0.904 is equal to our n. Oh, don't need that yet. That's on the next step. So that means your n is approximately equal to, once you plug that into your calculator, it'll be about 62 after you round it to the nearest whole number. And that is your initial bacteria. Okay, so you started with 62 bacteria and it's decaying. So after 4 hours, only 25 are left. That's basically what this says. All right. So I know that some of these were a little tricky. So if it helps, go back over them and kind of watch the process again. But make sure you understand that variables can change. Like you say, you have F of T here, or A of T, it changes to F of T. Instead of your initial size being N or P, it's N. You have your negative KT instead of negative RT. So variables can change. As long as you understand the concept behind it and know where to put what value, you should be okay. All right, so hopefully this made sense, and I'll see you on the next video.